This PowerPoint is going to be over the laws of motion. So the topics we're going to discuss are going to include the force, Newton's first law, Newton's second law, Newton's third law, the forces that are applied there, as well as gravitational force. We're going to talk about the application of Newton's laws, and then we're going to talk about the forces of friction. All right, so the four fundamental forces of the universe, there are actually only four forces. Everything else that you can think of, all forces, are some aspect of these four. First off, the gravitational force. Gravitational force is an unlimited force, meaning that it can go on forever and ever. So an object on one side of the universe can have a gravitational force on the other side of the universe. Electromagnetic is also an unlimited range, so basically you can have an electromagnetic force across the entire universe. Now, of course, the further away you get between two objects, the less force it's going to be. So while they can have a gravitational force on each other or an electromagnetic force on each other, you're never going to be able to measure that amount of force. The two forces that we didn't really know about except for the past 100 years is the weak nuclear force and the strong nuclear force. Now, the weak nuclear force is what effectively holds a neutron together from beta decay, and then a strong nuclear force is what holds the nucleus of an atom together, holds protons and neutrons together. Now these two, you can see that their range is actually quite small. Their range is actually inside of the nucleus of an atom. Outside of the atom itself, these two forces don't exist. They don't apply any force beyond the electron cloud of the atom. So anytime two forces or two electron or atoms are applying a force on each other, it's generally the electromagnetic force. Because if we look at the amount of gravitational force that's being applied, the amount of gravitational force is actually really, really small. So let's say we make gravity the standard of 10 to the 0 power. All right, so the amount of gravitational force is going to be 1. For that gravitational force, the amount of electromagnetic force is going to be about 1,000,000 times more than that. And then if we look at the weak nuclear force inside the atom, that's 10 to the 20. That's a really large force. And then the strong nuclear force, which is why we call this the strong force and this the weak force, because comparatively, the strong force that holds the nucleus together is very large. The weak nuclear force is still pretty large, but it's not as large as the strong nuclear force. But inside the nucleus of the atom, there is some electromagnetic force that holds an electron cloud, but the major amount of force is going to be this weak force and this strong force. All right, so a force is a push or a pull, and any object that is at rest needs a force to get it to start moving. Now, an object to keep moving doesn't need a force. Now, a lot of times you think, well, objects that are moving, we have to apply a force in order to keep it moving. Well, really, the only reason you have to apply a force to keep something moving is because we have something like friction that's being applied, basically a force that is pushing against it, trying to slow it down. Now, if we didn't have friction at all, then we wouldn't need that force in order to keep an object moving. This is Newton's first law. It basically says that an object in motion will stay in motion with no outside net force. But if we do have a net force, that net force is going to change its motion. And then the direction of the net force will be the direction of the acceleration. So if an object is moving forward, but the acceleration is backwards, then it's going to slow it down. The net force is going to be in the same direction as the acceleration. So the blue would be the net force, the red would be the velocity, and then the green would be the acceleration. All right, so this is an object of an example of something that would be moving with a slowing down because of the velocity being forward. All right, so the magnitude of the force is referred to as the amount, and then the direction obviously is going to be referred to as a direction. So the force is a vector, net force is a vector, and magnitude is the direction that the amount that's going to be applied. So a spring scale is actually something that can be used in order to determine the magnitude of the force being applied. And as that force is as a net force is being applied, then it's going to cause it to accelerate. All right, so Newton's first law again is referred to as the law of inertia. Inertia refers to the amount of mass an object has. As a matter of fact, the term inertia is the same as talking about an object's mass. So mass and inertia are the same thing. Can't really write that too well, but you see that the amount of inertia determines how much acceleration an object is going to have when a force is being applied. So every object continues at a state of rest or a uniform velocity. Now what a uniform velocity means, it means a straight line velocity with the same amount of velocity the whole time. All right, so as long as no net force is being applied, it's going to keep that uniform velocity. And really, if you think about rest, being at rest is a uniform velocity. It's a uniform velocity of 0 meters per second. All right, so if I apply a force on this book and there's a force of friction applied against it and the net force is 0, then whatever velocity it has, it's going to keep that velocity the whole time. So if it's moving, it's going to move at a constant speed, or if it's at rest, it's going to stay at rest. So that means that with no net force doesn't mean no forces at all. No net force means that all the forces that are being applied, whether it's no forces or 2 forces or 10 forces, all those forces are balancing each other. And if all those forces are balancing each other, then that means there's no net force and it's going to move at a constant speed, whether it's at rest or at some velocity. All right, so take a second and read this question and see if you can answer it. So when you sit in a chair, the resultant force on you is going to be 0 because you have no net force being applied to you. Effectively, you have the chair pushing up on you and you've got gravity pulling down on you. If those two forces are balancing each other, you have no net force. You're going to have a net force, a resultant force. Now that's another term for net force, is a resultant force. Okay, so these two forces being applied to you, they balance each other, gives you 0 net force. All right, so this brings us to Newton's second law. This relationship is a relationship between acceleration and force. The amount of acceleration is proportional to the amount of force and inversely proportional to mass. So that gives us this equation right here. Now this symbol right here is a Greek letter sigma, and that Greek letter sigma means summation. So it means summation of forces, meaning you add up all of the forces, and once you do that, that's going to be equal to mass times acceleration. Now if you remember, adding forces being a vector, then that vector will give you one net force, and then that direction of the net force would be the same as the direction as the acceleration. All right, so net force equals mass times acceleration, and since it's a vector, then we have to do the net force in the x direction, net force in the y direction, net force in the z direction. If we ever get anything that's three-dimensional, then we got to do the z direction as well. For what we're going to be dealing with most of the time, we're going to stay in the x and y directions. But that means that if you have a force that's at an angle, then you have to break that force into components. You got to figure out which part is in the x direction and which part is in the y direction, and just deal with those two directions at the same time individually, because each direction, the x direction, y direction, are independent of each other. So if you have a force that's in the x direction and a force that's in the y direction, they're not going to affect each other. So in the x direction, you got a force that is in the positive direction, a force that's in the negative direction. They subtract from each other. Technically, this one being negative and this one being positive, they add with this being adding a negative. But if you have a y direction force, then that doesn't affect either of these forces in the x direction. You just keep these separate. But the y direction force, at the end, what you do is after you add your x direction, and let's say you have another y direction force, you would add these together because they're both positive. All right, so you take those and add them together. You take these x direction and add them together. Then you would take your resultant, which you would have a total in the x and then a total in the y, and then use your Pythagorean theorem in order to figure out the direction, and then inverse tangent to figure out the angle. All right, so the force being a vector, which means net force is going to be along the coordinate system for each direction, x, y, and z. The units for forces is going to be the SI units for forces is going to be a Newton, which is a Newton is a kilogram meter per second squared. Now, if you use a British system, you get a slug for mass. You may have heard that term before, but a slug is a unit of mass, and pound is a unit of force. Now, in our society today, we like to use the word pounds to refer to mass and weight, and we'll talk about weight in a second, but pounds is technically just force, which is weight. A slug is mass, and there is a huge difference between mass and weight, and we'll get into that later. But for the SI system, the International Standard System, kilogram is what we're going to use. We're going to stick with that, and then meters per second squared for acceleration, and then a newton is going to be our unit for force. All right, and that's going to be kilogram times meter per second squared. So acceleration being meter per second squared, mass being kilogram, you multiply those together, you get newtons. So in this example right here, it says a man stands on a scale in a stationary elevator. So the elevator is not moving. We'll talk about why he's on an elevator in a minute. But if he's standing on the scale, then he has two forces that are acting on him. He has a downward force of gravity, and then he has an upward force, what we call a normal force. Okay, so we got force of gravity, which is mass times 9.8, and we haven't really talked about that. That's referred to as his weight. Sometimes it's a capital W used for that. I generally like to use an F to designate any force, and then for the force of gravity, I'll put a G as a subscript. All right, so the force of gravity is equal to his mass times the acceleration due to gravity. On Earth, the acceleration due to gravity is 9.8 every time. Now you may say, well, isn't it negative? It is. And when we deal with this vector in the equation, we'll add the negative. But for right now, to find the weight, we'll just take mass times 9.8, and we'll deal with a number, and then we'll get the direction when we start dealing with the equation. All right, so normal force. That upward force is called a normal force. Now, where does the term normal come from? Normal is actually a mathematical term that means perpendicular. Normal is a math term that means perpendicular. So when referring to this force right here, we're referring to a perpendicular force to the surface. And the normal force is always perpendicular to the surface. Now, what's interesting about that is if we take this surface and we actually slant it, we tilt it, then the normal force will also be tilted. It'll still be perpendicular to the surface. Okay, so going back on all this, erase it all so we get to what we're doing. Okay, so if you take your normal force and you have minus the force of gravity, so look at the direction on these, right? The normal force is up, the force of gravity is down, and we include that direction in the equation right there. So that's why we don't put a negative with a 9.8 here, because we'll include it when we start adding the forces together. All right, and then if you take that mass times gravity to the other side, you see the normal force is going to be equal to mass times gravity. So the scale is going to read equal to his weight. Now what's interesting about this is a scale doesn't actually measure weight. A scale does not measure weight. Now you may be like, well, of course I use a scale to measure my weight. But think about this. A scale pushes upward on you. So when you set a scale down on the floor and you stand on it, it applies an upward force. Force of gravity, your weight, is a downward force. So if the force of gravity is downward, then the scale pushing upward does not measure your weight. What you do is you use Newton's second law in order to figure out what your weight is by not accelerating. And when you're not accelerating, the upward force of normal force is going to be equal to the downward force of gravity. So what if we are accelerating? All right, so that's why we're going to get to while we're on an elevator. So let's suppose we're moving upward at a constant velocity. Okay, so a constant velocity upward, that constant velocity means that there's going to be no acceleration. So when we do Newton's second law, the forces acting on the man, again, are the upward force of normal force, the downward force of gravity, and then the mass times acceleration. All right, so again, the downward force is mass times 9.8. The upward force is the normal force. So let's go ahead and plug into this equation. Normal force up, force of gravity down. The acceleration 0 because we're dealing with a constant velocity, All right, so the normal force minus the force of gravity. The minus is because of the direction of the force of gravity. It's going to be equal to mass times 0. And again, the normal force is going to be equal to the scale reading because there is no acceleration as you're moving at a constant velocity. Now in this example, it says that we have a constant acceleration. So we have an upward acceleration. With this upward acceleration, that means we're going to have a net force. And when you have a net force, forces are not going to be balanced. Net force of 0 means forces are balanced. When you don't have a net force of 0, they're not being balanced. So forces acting on the man, again, you got the downward force of gravity, the upward force of normal force. You go ahead and do your equation. Net force is going to be equal to mass times acceleration. Now this time we're going to keep something on this side of the equation because we do have an acceleration. So normal force minus the force of gravity, mass times 9.8 is going to be equal to mass times acceleration. So to find the scale reading, what the scale reading is going to be, which is the normal force, we're going to take this mass times 9.8 and take that to the other side. And that gives us a positive. So mass times gravity plus mass times acceleration. We factor out that mass and we get that mass times gravity plus the acceleration. That'll be equal to my normal force. Now let's think about what this is saying logically. The scale is going to read more than the person's weight. Okay, how do I know that? Because the person's weight is mass times 9.8, and when you add something to this, because that acceleration is positive, right? With a positive acceleration, you're going to have an increase. You're going to have an increase in your value over here. So with that increased value on this side, you're going to have a normal force that's greater. Okay, now let's think about that conceptually. If you're accelerating upward, then that means you have to have an upward force that's more than the downward force. A normal force, which is upward, has to be greater than the downward force because your net force, your acceleration, is positive. It's upward. So the scale is going to read more than your weight. So in this problem, let's say that we have an acceleration downward. So our acceleration is negative. So we have a negative acceleration. All right, so let's move on. Let's see, forces acting on the man. Of course, we got force of gravity down, normal force up. Net force is going to be equal to mass times acceleration. So let's start plugging this in. Now, instead of just putting acceleration, let's actually put that negative in there, right? Negative acceleration, which is downward. Now, what's interesting about what they did here is they changed the convention. Now we're used to saying, well, up is positive and down is negative, but what they did is they said that down is actually positive. So if down is positive, then that means that the force of gravity will be positive, and then the normal force will be negative. There's nothing wrong with that, because remember, if you remember, convention is basically us agreeing on what direction is positive, what direction is negative. But because it's a convention, it doesn't have to be that way. Sometimes we change our direction of what's positive and negative to make the math easier. And this definitely makes the math easier because the acceleration being downward, then our net force is going to be downward. So we're going to get a positive net force, but that means that effectively, since we change the direction, it's going to be downward. All right, so rearrange your equation. You take your normal force to the other side, then subtract your mass times acceleration over here, and then you factor out that mass, and you get that mass times your acceleration due to gravity minus acceleration, right? So now you have a net force downward. Well, with a net force downward, then that means that you have to have a downward force that's bigger than the upward force. But keep something in mind, your downward force does not change. Your downward force is your weight, and your weight doesn't change as long as your mass doesn't change and the acceleration due to gravity doesn't change. So the only way the scale will read less than the force of gravity is if your scale itself decreases. So the scale reading will decrease, and it'll read less because of that negative acceleration, that downward acceleration. All right, so take a second, read this question, and see if you can answer it. All right, so a constant net force acts on an object. Describe the motion of that object with a constant net force. Now, the idea is that you have a net force. Net force means that you're going to have an acceleration, right? So it's not going to be a constant speed and not going to be a constant velocity, because a net force produces an acceleration. Now, because it's a constant net force, then you're going to have a constant acceleration, not an increasing or decreasing acceleration. All right, so constant acceleration because you have a constant net force. That's Newton's second law, net force equals mass times acceleration. All right, so in this question, it says that there's a force being applied, and let's assume that is the only force that's being applied. And you have an object that is starting at 0. It takes 5 seconds to get to some velocity. We don't know what that velocity is. The force acting on it is going to be 20 newtons, and since that's the only force, that's going to be the net force. And then we have a mass of 5 kilograms. All right, so net force equals mass times acceleration. They kind of skipped a step here where they dropped the summation because there's only one force acting, right? Now, That's going to be equal to mass times acceleration. I don't have the acceleration, but what I can do is I can use kinematic equations in order to determine what the acceleration is. Acceleration is going to be change in velocity over time. So we can plug that into our equation here, mass times acceleration. Then we go ahead and put that in. We get mass times change in velocity over time. The change in velocity is final velocity minus the initial velocity divided by time. All right, now we're trying to figure out the final velocity. All right, we want to get to this variable right here. So we need to get everything else on the other side. We divide by mass, multiply by time, and then we're going to add our initial velocity. Now you notice they don't have the initial velocity in here, and that's because our initial velocity was 0, so they basically just dropped it. All right, plug in our numbers, 20 times 5 divided by 5, that gives us 20 meters per second for the final velocity. All right, so average force required to stop a 1,100 kilogram car in 8 seconds if the car is traveling at 95 kilometers per hour. So we got a mass, right? And we got a time, and we got this velocity here. Now it's traveling, and what we need to do is we need to stop, right? So this is an initial velocity, and then our final velocity is the velocity when it stops. All right, so mass, time, final velocity, initial velocity. All right, so final velocity, initial velocity, and time, that can give us acceleration. And to find average net force is going to be equal to net force equals mass times acceleration. That's Newton's second law. All right, so the average force or average net force is the total force acting on it. Because we're moving forward, right, we have this forward velocity, and we're going to have an acceleration backward, which means our net force is going to be backwards. All right, so go ahead and plug this in. We got the final velocity equals initial velocity plus acceleration times time. These are two equations that's going to help us to get to our average net force, okay? Because we need to solve for acceleration here, and then plug that in for our Newton's second law, and we get mass times this value. So we got everything here. Now there's a slight issue here, right? The final velocity is 0, okay? So that goes away. But the initial velocity is in kilometers per hour. Kilometers per hour. We have to convert that. That's got to be in meters per second. Now when you convert that meters per second, 1 kilometer is 1,000 meters, and then hours is in the denominator here, so hours converted to seconds. All right, so we multiply everything on top, divide by everything in the bottom, and you get that the net force is going to be equal to negative 3,600 newtons. All right, so read this question, see if you can answer it. It says a net force F accelerates a mass m with an acceleration a. If the same net force is applied to a mass of 2m, then the acceleration will be what? Well, first off, if you think about an object's inertia, so you have the same force, but it's applied to more mass. Now, think about your experience. If you have one object that is light and one object that is heavy, which one are you going to be able to accelerate more? Right? The light object, the one with less mass, is easier to accelerate. So the one that has more mass should have a smaller acceleration, which means that A and B are out. All right, so with a smaller acceleration, it's either C or D. Now, if you think about the equation, Newton's second law says net force equals mass times acceleration. So the force is constant. The force is the same on the left side. So if I have twice the mass, then I need to get rid of that 2 in order to give me the same amount of force. So I have to have half the acceleration. All right, so net force equals mass times acceleration. With twice the mass, that would give me half the acceleration. All right, so again, twice the mass. As the mass doubles, the acceleration would be half, and that would give me the same value on this side, the same value for the net force. All right, so this cable supporting a 2,125 kilogram elevator is a maximum strength of 21,750. What's the maximum upward acceleration that can give the elevator without braking? All right, so we're looking at the upward force that is needed, okay, because that upward force has a maximum, and there's the maximum right there. Now that's not the net force, that's just the upward force. So if you just did mass times acceleration to get your net force, that would not give you the answer because you also have the weight of the elevator being applied to it. All right, so let's go through this. Set up the scenario. You're trying to find your acceleration with mass, tension, and gravity. So you've got your object here. All right, so we're going to talk about a little bit about free body diagrams. We actually made a couple before, I just didn't refer to it. So let's talk about it here. A free body diagram is a diagram where you have a mass, an object, where forces are being applied to it. Okay, this is a terrible dot. Let me redraw that. All right, it's kind of hard to, yeah. All right, so if you start with an object represented by a dot, then the forces being applied are going to be applied to this dot. So we got a mass at this object that is that has the upward force of tension, and we'll call that. I like to use again the capital F to designate a force, but I'll put a sub T for tension. That's the cable it's pulling up on it. And don't forget we have gravity pulling down on it. This is the force, kind of ironic really. Everybody remembers gravity when talking about free body diagrams, but they forget to include it in the equation. All right, so this is your force of gravity. So Newton's second law, net force equals mass times acceleration. So you got your tension upward, right? And then you've got your force of gravity downward, which is mass times acceleration. Now we're going to have an acceleration upward. So we go ahead and add our forces together. Now notice again, we put that negative in there for the force of gravity, but the maximum tension, right, is going to be that tension that's given, and we need to figure out our acceleration. All right, so to solve for our acceleration, simply put, we divide by mass. We have the tension is 21,750. We have mass, which is 2,125 times gravity, which is 9.8. And then we divide that by the mass of the object, which is 2,125. And we get an acceleration is going to be 0.44 meters per second squared. So with this cable, if we have any acceleration greater than 0.44 meters per second squared, it's going to snap, because that requires more upward force than what the cable can supply. All right, so how much tension is in a rope if you stand, let's see, use an acceleration of 1,200 kilogram car vertically upward at 0.8 meters per second squared? All right, so how much tension's in a rope? Accelerate a car vertically upward. All right, I'll give you a second to go ahead and pause the video and see if you can answer this. All right, so let's go through this. We need to find, let's see, how much tension. We're looking for tension, right? So our force of tension, that's what we're looking for. We're given the acceleration. We're given the mass of the car. So when we're talking about forces, that's going to be Newton's second law. Net force equals mass times acceleration. So we've got to find the tension with respect to mass, acceleration, and we're going to have the acceleration due to gravity as well. All right, so the tension of the object, the car being held upward. I don't know really what scenario this would happen in, but let's say we do. We got something that's lifting a car. Net force equals mass times acceleration. All right, our free body diagram says we have an upward force of tension. We got a downward force of gravity. All right, and the acceleration is upward. And again, the acceleration is given right here, upward of 0.8 meters per second squared. So what's the force of tension? So tension minus the force of gravity, which is mass times 9.8, is going to be equal to mass times acceleration. You go ahead and take that mass times 9.8 to the other side, plug in your numbers, solve for tension, and you get what looks like 13,000 newtons. 13,000 newtons, that's 1.3 times 10 to the 4th newtons.